Hello, everyone, and welcome to this first webinar on RL. Um, so just making sure that everyone knows where it is. Live channel. So I thought today what we would do was to start off by talking a little bit about MDPs and talking a little bit about how we can so there's three algorithms that I would like to talk about. One is uh, policy evaluation, policy improvement, and finally policy iteration. And without further ado, I think the way I had planned this session would be that we would look at some of the pseudocode for the methods, and then we would look at how it would be implemented in Python. So, all right, let's start. So the first thing is, let me just share my screen. Uh, does not seem to have a, right, so it doesn't seem like there is a share screen, but so okay. In that case, I think the way I'll do this is that I will just speak about it and hopefully you can follow along. Okay, so the first algorithm is called policy evaluation. So I guess it would be the first starting point. I guess it would be we should talk about what a MDP is. Um, and an MDP, which stands for Markov Decision Process, is basically a structure of modeling an environment. And when I say modeling environment, the MDP consists of states and what you call transition probabilities. These transition probabilities tell you what the probability is of transitioning from one state to another state. And the other state can also be it returning to itself. So let's say you have state 0, 1, and 2. So you can go from state 0 to state 1 with a probability of a half. And you can go from state 2, 1 to state 1 with a probability of a half. So you can remain in the same state with the same probability, and you can also go to the you can also go to the same to another probability, it's another state with the same probability. So why are we talking about MTPs? Because MTPs is the bread and butter of a lot of these reinforcement learning algorithms, or at least a lot of these traditional reinforcement algorithms. Because so when we talk about, for example, our first algorithm, which is policy evaluation, what we are essentially saying is we would like to know what the value is for each state in the Markov decision process. So we would like to know what the value of being in state 0 is, what the value of being in state 1 is, and what the value of being in state 2 is. And that way we can basically derive, so that way we can derive like, so we're going to use this policy evaluation so that we can actually create a policy improvement as well. Right, so So the way we're going to do this is we're going to use, um, we're going to start off with initializing a value function, which we will do by just putting, so for each state, we'll just give it an initial value of 0, right? And then we will repeat this. We'll start by giving delta, which will be a variable that we will just set to 0. And then we will, for each state in this Markov decision process, which is an MDP, we will do the following. We will set the value function for the state. So the value of that state, we'll set it to v, to a small variable called v. We will then take this vs, so which is the value function for the value of the state. We will set that to the probability of transitioning from the state S prime, which is the new state, uh, with the reward R, given that we start in state S and with an action A. And then we're going to multiply that with the current reward plus the discounted value of the next state. So we'll do this for all states and sum them up. And then we'll take the probability of taking action A given that we're in state S, and we'll do this for all the available actions for that state. So every state will have available actions that you can do. So let's say you're in state 0, you can go right, you can go left, but you can't go up. So you'll have left and right. And those are the ones that you are then summing over, right? So you get this new value of state S, and then you take, so you said delta will be equal to the maximum of this new delta, sorry, the old delta, with the difference of the old value function minus the new value of that state S. And you repeat this for each state. And I know this is a bit confusing because it's hard to really say without really being able to show you my screen. It's hard to really explain the equation. I think it's easier when you're just actually looking at the equation. I mean, but yeah, I mean, so you repeat this until the difference between the new value and the old value is very, very small. So this is policy evaluation. The reason we need this is because given a policy, what we want is we want to know what the value of being in each state is, right? So now that we know that, how can we use this to improve the policy? So now we've created a value function, or we've derived a value function using this algorithm called policy evaluation, and we are now going to use this policy, this evaluation to improve the policy. What we'll essentially be doing is we will basically start with the policy, right? And sorry, we'll start with the value function that we derived, and we'll start with the MDP, so the Markov decision process, which is essentially in a modeling of the environment, and then we'll output a new improved policy. We'll do this by first deriving the state action, so the value action function, which is the Q function. Essentially, you take in input state and action, and it will give you out a value for. And the proper interpretation of the Q value function is that what is the value of what is the value of a state and an action, right? And the way you think about it is you taking the state, and that you take this, you're in a state, let's say S, which is 1, and then you take the action right, and then after that, after you've taken that and you've arrived in a new state, you just follow the policy. And that is essentially what the Q function is. So we'll use the Q function to basically take the action with the highest value for each state. So you have state 1, 2, 3, 4, 5. State 1 will have the state 1 will have a bunch of values for each action, and you will take the action that has the highest, and that way you'll get the highest policy. Once we have that, what we can do is, so that is the policy improvement algorithm, essentially. In a nutshell, that's basically what we're doing. But once we have that, we can now use these two algorithms that we've created, the policy evaluation and policy improvement algorithm, to get another algorithm called the policy iteration. So what we will do is we will toggle between policy evaluation and policy improvement. We'll first evaluate a policy, derive a value function, use that value function to create a Q function and improve the policy, and then value the value function again, and then evaluate the policy, and then derive a value function, and use that value function again to improve the policy. And we'll keep toggling between those two states until we reach a optimal policy. And we'll find out whether we'll stop when the old policy is the same as the new policy. So yeah, and that's basically the three algorithms in a nutshell.